Good afternoon. My name is Jean-Louis Briot. I'm the Spencer J. Buchanan Professor in the Department of Civil Engineering at Texas A&M University. I wish to welcome you to the 9th Buchanan Lecture. In a short while, I will invite Professor Niedzwiecki to say a few words of introduction. Before that, I wish to do two things. First, I wish to introduce the new member of our Texas A&M University geotechnical team, Dr. Giovanna Biscontin, and then I want to go over the program. Our geotechnical team has fuzzy boundaries, since many in the department have a geotechnical engineering interest and background. The core of our team, however, is made of Dr. Litton, who is our senior member, Dr. Murph, our offshore specialist, Dr. Albany, our numerical simulation wizard, Dr. Biscontin, our beautiful new addition, and myself. Of course, we don't want to forget our emeritus geotechnical faculty, Drs. Coyle, Thompson, and Dunlap, also known as the Three Musketeers. While we're on the geotech program, I want to mention a major event coming to Texas A&M University. The first international conference on scour of foundation will take place at Texas A&M in November 2002. You can take a brochure at the door if you wish. You may have seen it as you came in. There's a lot of business to be done by geotechnical engineers, not only in research, but certainly in practice as well in this area. If you feel that you do not have the enough background on this topic, there will be a one-day review course on scour foundations on the Sunday before the conference. Now the program. After Professor Niedzwiecki's remarks, I will have the pleasure of introducing Professor Landva. He will follow with his lecture on behavior of waste fills. We will then take a time for questions. I regret to tell you that Dr. Hook, who resides in Vancouver, called and canceled his lecture in light of the events of September 11. His lecture is in the September issue of the ASCE Journal of Geotechnical and Geo-Environmental Engineering. I have read it and highly recommend it for those interested in big tunnels in bad rocks. I will then have the pleasure of introducing Professor Holtz before he delivers his lecture on geosynthetics for soil reinforcement. A question period will follow and will be led by Mr. Darrell Hooper. Finally, Dr. Philip Buchanan will thank the Buchanan Lecture. At that time, we'll take a series of pictures. After the pictures, you're all invited to my home for a reception. You should have a copy of the map on how to get to my house. There are some in the front. The guest book, I'm going to circulate it in a minute. If you could simply put your name and print your email address, I would appreciate. Next year, we will use email contacts and we'll have a website. The location of the website will be within the Texas A&M University website under Civil Engineering, then go to Briot, and it will be within my website. http://ceprofs.tamu.edu/Briot. Professor Niedzwiecki is the head of the Department of Civil Engineering at Texas A&M University and the Woodford Kane Professor in the department. Let me now ask Professor Niedzwiecki to give us a short summary of the state of the Department of Civil Engineering at Texas A&M University. John?
Thank you, Jean-Louis. My slide tray didn't make it. There were 50 slides that I wanted to go over to give you that brief presentation. so I'm sorry it's not here. Things are going quite well, I think, in the department. We have an outstanding group of faculty. The advisory council has just been absolutely superb. And I think there's a spirit with the students. We still have been blessed by having 870 undergraduates in the civil engineering program this year. We oscillate around 900 annually, and so I don't think we're too far off. In the graduate program, we have 270 students enrolled in civil engineering, and that's slightly off. It's around 300. So next semester, maybe it'll be a little bit higher. So I think you can get an idea of the size. Lots of activities going on. We're rebuilding the geotechnical facilities. I hope some of you will have a chance to come and see the new laboratory. That was quite an experience dealing with this geotechnical faculty deciding what went in there. They have some expensive taste, I must say. And I don't want to disappoint them, because I'll be coming to visit some of you to try to make some of these things reality. We have a strong commitment. This is one of the most fundamental areas in civil engineering, and we're going to see that it succeeds. And I think you can see the faculty. You know, having Don Murph, I wondered how you're going to get, if Bob Litton was a senior, then I wondered what Don was. But we can talk about that later. A very enjoyable faculty, and I think we've come a long way. There's a long way to go. We're going to have a coastal laboratory facility built, which is in the ocean area, and John Louie's been instrumental in getting some support from the Texas Transportation Institute, where he can do larger scale scour studies, and we hope that facility will be open in time for the scour conference. In fact, we're planning a reception there, so Jean Louis and I will be there. I'm not sure that the building will be completed, but we'll be there. Let me just say a couple words of thanks again to you. You know, when I go out and visit with the former students, it's to inform them about what's going on in the department, the kinds of things that our faculty are doing, the achievements of our students, and many of you have responded by providing help in terms of scholarships and funds that we use for student activity fee, travel, whatever activities that they want, and I wanted to thank you very much. I have one other person I want to thank here, and John Louis is always giving things out, so I decided today that I'd do things differently, and I'd bring something for him. So John Louis, would you come up here? My slide tray hasn't arrived yet. John Louis. Wow. Huh?
Thank you, John. Thank you, John. Now it is my pleasure to introduce Professor Landva. Professor Arvid Landva received his bachelor's degree in civil engineering from the University of Strathclyde in Glasgow, United Kingdom in 1956. A doctorate from the Norwegian Technical University in Trondheim, Norway in 1962. And a PhD from Laval University, Canada in 1980. Between 1956 and 1963, he worked at the Norwegian Geotechnical Institute, where he developed the simple shear test with Lauritz Bjerrum. Then he moved to Canada, first as a geotechnical consultant on the very large Mactaquac power project, then as a professor at the University of New Brunswick until 1996. Throughout his career, Professor Landva has been an active consultant, and since 1996 has worked with Gemtech Limited. He dedicated his professional life to the understanding of non-textbook soils, such as peat and waste fields. Among other professional recognitions, he received the 1985 ASTM Hagen-Togler Award and is a Fellow of the Engineering Institute of Canada. Now, I need to add that I have waited for about 29 years to introduce Professor Landva, to have an opportunity to introduce Professor Landva. There's a French saying, patience et longueur de temps font plus que force ni courage, which is a fancy way of saying, be patient, you'll get there. You see, Professor Landva was my master's advisor, and I have many stories to tell. I selected a few. I arrived at the University of New Brunswick on September 1st, 1972, and met with Dr. Landva, who told me, Brio, go paint the drill rig. My English was very bad, and I thought that he had misunderstood who I was. So I explained again. He said, Brio, go paint the drill rig. I gave it another shot, mumbling things like mathematics, differential equations, master's degree. Dr. Landva replied, Brio, go paint the drill rig. So I did. And I learned more about drill rigs by painting it than in any other course I ever took. He knew that, of course, and was always for me a very thoughtful teacher, one who cares as much about fundamentals as he does about practicality. Then after the drill rig effort, Professor Landva told me, Brio, 3 months in the field. Again, I was surprised by this unexpected approach to education, but drove regularly with the technician to a swamp where we were running sampling and in situ tests on deposits of peat. I became so involved with peat mechanics that Dr. Landva called me jokingly a peatnik. Of course, shortly thereafter, I asked him not to use that joke anymore for Pete's sake. Overall, Dr. Landva was thoroughly unimpressed with my performance and has told me many times, Jean-Louis, when you first came and for many months, you were rather hopeless. But then you met Janet and something clicked. Tell her I want to dance with her. So it seems that Arvid is much more impressed with my wife than he is with me. What he does not know is that my wife is still totally unimpressed with me. The title of his lecture is Behavior of Waste Fields. Please welcome Professor Arvid Landva.
Thank you for your kind words. Well, maybe they weren't all that kind. And thank you for inviting me here. I think that's quite an honor. I'm really not quite as bad as he tells you. Today I found, or this year, I was just thinking about it, is sort of an anniversary. When I met Jean-Louis when he came to UNB, that was, I had been 1 year in peat research. So that, and then I did that for 20 years, exactly 20 years. And then now I have been doing research on waste fill, which I simply call garbage. Calling a spade, for 20 years, from 81, that started, and until 2001. So I have a few things to tell you, and there are so many new things here. We were discussing presentations at breakfast today, and how they vary. Some people have a lot of slides, and some people are known to have no slides at all. They just talk and in a very entertaining way. I have to go the slide way, or PowerPoint as it is, or both, because, as I said, there are so many new things that I really need these things to show you. And we can start right away with slides. First of all, I want to show you what material we're talking about. This is garbage. It is Jean-Louis tells me that I'm very good at presentations. In fact, it borders on excellent. But I'm excellent in telling people what not to do, he says. And he said, please don't do that this time. Well, I'm going to at least tell you, or suggest to you, that this material does not lend itself to vein testing. It doesn't even lend itself to the Briot pressure meter. It doesn't lend itself to almost anything. This is what it looks like when you dig test pits, and there's not much you can do about it. That happens to be a trophy that I just found, an old hot water tank. It's possible to use augers, and I ended up with a minimum size 6-inch solid stem augers. You can get samples in just about any garbage, and I've tested them all the way from Paris to Vancouver to Florida. If you use a Becker drill, though, well, you shouldn't. That's what's going to result. It's going to get plugged right away. So to use a Becker drill in garbage, in landfill, seems to be impossible. I certainly wouldn't recommend it. Compaction in garbage, in landfill, certainly is related to compaction, ordinary, regular, conventional compaction, but usually what you do or always compaction is one of getting the grains closer together. In garbage, you want to crush the grains, and so these pellets here, you will see when you let the right kind of sheep's foot type roller compactor on it, you crush the thing, and you do the same with the steel drums. They practically disappear. And if you don't do that, of course, you're ending up with a whole lot of voids in the landfill, which you don't want, because it will deteriorate, it will decompose. Classification of this stuff means that you simply have to separate these things apart, take them apart, and this happens to be, now into. If you can't see, if you can't read, it doesn't really matter. What matters is that you have all these different constituents. Paper usually is about 40 to 60%, and so on. The technique that I finally ended up with was to take samples either in test pits with an excavator or a backhoe, or with a bucket auger. Fairly expensive, of course, but that works. And then reconstitute the samples in the lab to the same density, and then test it. That you're looking at now is a compressed garbage, compressed fill, refuse, and it's pretty dense when it is compressed. You, in fact, don't see any voids. The void ratio of a compressed garbage is very small, and it means, for example, one thing it means is that the water content is not all that important with respect to unit weight. And finally, we're looking at sort of a little bit of a Mickey Mouse, but a large-scale percolation test, where I just got hold of one of these big tanker trucks, and then used a little backhoe there and filled it with water and did the percolation test. This one is from National Geographic. Of course, their graphics is just excellent. And for those of you who don't often deal with landfills, you can see how it's done. You can see how it's placed in lifts, often about 10 feet thick, and they can either place it from the top, and then the compactors walk down the slopes, or from the bottom and the compactors walk up the slope. But usually they turn anyways, so that they cover it with several passes. Another graphic from National Geographic, you can see that here we have 50% paper. This one here is not necessarily, you have to expect that this varies. You can't say that this is wrong or that it's off or anything. You'll find garbage just like that, and you'll find it different with paper, maybe 20% and so on. But what they have in common, though, and I'll get back to that on settlement, is that most of it, if not all, will decompose. as part of the settlement. On the left side, you see a 25-foot deep test pit. You can't often do that if you hit water. And then you see an auger, a bucket auger, which typically is about 30-inch diameter. We're not talking 2-inch here. It has to be large, so that you can also measure volume and weigh the stuff and get the unit weight. And on the right, you see a bunch of graduate students. And they are very nice to to turn to when you have to classify the stuff. And they are separating and having fun. Another graduate student who survived, and he has a pretty good job. Garbage, when you read papers about garbage or landfill or refuse or MSW, whatever you want to call it, then you often find a whole lot of negative stuff. People saying how difficult it is, how difficult it is to determine things. It's not quite as hopeless, I think, as people seem to think. For example, we know pretty accurately the specific gravities, or as I've called it here, the unit weight of the solid constituents. We know those. We know that the paper products, the paper is organic. So organic is 14, and if you're not used to kilonewtons per cubic meter, then 14 would correspond to what, about 90 or something like that. 70 is of course metal, that's steel, that's very high, so it's about 7 times 62, so it's over 400. And you're all familiar with these things. We know the specific gravities. If we now could just separate these things, and we can do that, given enough graduate students, then we can actually calculate the average specific gravity. And from then we can go to, back to soil mechanics, and we can find out void ratios, except we do have to distinguish between intraparticle and interparticle. That's between particles or constituents and inside them. The colored portions are 3 constituents, just picked at random, 3 different ones, and you don't have to read the equations, and it's not difficult to understand, of course, because what the first one says is that the density is equal to the mass divided by the volume. So there's nothing new, except now you have 3 different masses and 3 different volumes of them, and we can pretty much measure that. We know the densities, and we can weigh them. So since we can weigh and since we know the densities, we can find out the average density, which is the last equation there. Just a summation of all of them. And densities, up till really just very recently, I had the same tendency as we all seem to have. We look at some figures and we say that's not possible. Our theoretical considerations show that it can't be so, and so on. I have tried to stop doing that and actually looking at results. All those yellow dots there, the little squares, are measurements I did myself. So I know that there's no cheating or I just took the thing up, excavated it, and weighed it on reliable scales, which at times I made sure were calibrated. And I measured the volume with the thing we tongue-in-cheek called the pitometer, which was just a long stick with what happened to be a pump down there, and we measured the diameter, or rather the width of the pit, and the length of it, and so on. And we measured these things 50 different points, and then it was fairly reliable, I would say. And you see those results there. Now, it's very typical to say that the unit weight of and it's very important, of course, for stability calculations of the stuff that is underneath this. For example, the fresh kilns on Staten Island, 500 feet thick. It will never fail, in my opinion, within the garbage. But underneath there is a soft clay, and that might fail if you're not careful. And of course, then it's going to be extremely important to know what the unit weight of this stuff is, and also what is the lateral force that it can exert. So we have these two things that we have to find, and I think I have found those, and I now believe those high values. You shouldn't use for a landfill. You shouldn't use less than 90 pounds per cubic foot. I would say if you do those things, and you wouldn't be wrong if you went higher than that. 128 was done in the operating industries landfill in Los Angeles, or near Los Angeles, and they tended to ignore them because they were so high, and so we are so wise, we know how to use computers, and the computers tell us that that's too high. I have started now to believe it. I don't think we can afford not to. It was the test, these tests cost hundreds of thousands of dollars. 1 point is very, very expensive. So there you see, and you will see it when the paper is ready, which I will, I promise to prepare it, Jean-Louis, but I don't have it here. In the field, in the lab, we do testing with large scale. So 11 by 17 is a minimum, like a foot long and a foot thick and or more, because the material is of course rather coarse. That one is used to be a direct shear, but I fixed it up so that we could use it as a simple shear. Simple shear before the shear, after compression and before the shear, and after about 1 inch of deformation or displacement. But of course the difference between direct shear, one important difference between direct shear and simple shear is that in simple shear you will know the actual strain, the shear strain, which is equal to the horizontal displacement divided by the thickness of the shear zone. And you know what the shear zone is more or less exactly. So you can get that. Just another picture of compressed garbage. It looks different. You will recall the first slide I showed you, all that stuff. And now this one it's very, very dense. No wonder it has a fairly high unit weight. The shear, if we now go back to direct shear, there is a tendency to always use C and phi, or I think as you Americans call it, phi. C and phi, I mean, it's there to stay, so there's not much we can do about it, except that I insist that these values will depend on the direction of shear. And you can just think about the deck of cards. If you try to shear it in direct shear or in simple shear, along the cards, of course, it's very, very easy to do that. But if you try to shear it across the cards, you will have some problems. And here you have to the left dry horizontally stacked, so that reached failure, sliding, that is, at whatever you see there, the shear stress, whatever it is, doesn't really matter. What matters is that when you now go to the vertically stacked paper, on the right there, it is a whole lot greater than, in fact, we couldn't test it. We would have failed the apparatus, I think. So we just had to give up when we got to 50% and 4 or more times the shear of the other one, and it would have been impossible to fail it. So we should learn something from that, considering now that you have seen how landfill is made, how it's placed. We know then that parallel to the lifts that are placed with the trucks and the compactors, the shear strength is at its minimum. and across it's at its maximum. So that it's important then to find out how did I place the landfill, and often you can find that out. In another diagram, you can present this in a different type of diagram. So and here are our beloved C and phi values, which people seem to like so much. So if you have dry horizontally stacked paper, you have no cohesion and a very low friction angle. And if it's dry, if it's vertically stacked, then it's practically meaningless because you just cannot even measure it in the apparatus we have. Typically, that is a curve of both direct and simple shear. With respect to the, I have done a little bit of fudging here in order to get the two, but I'm reasonably sure of the deformations. I've used shear strain here on the abscissa, and you cannot measure shear strain in a direct shear test, of course. So a little bit of fudging, I've done that. The simple shear is correct. The direct shear was pretty well put on top of that, and it happens that the direct shear goes very much, further. It goes to much higher strain. The simple shear stops there, and the direct shear stops there. And typical though of this, and I found the same thing with other materials, but that will be another lecture. But I have found the same trend for Norwegian quicklay, for rockfill, and for peat. They always seem to have this bend, and I remember discussing that at some length many years ago with Bjerrum in the lab. He and Kjærnsli were discussing this, and we never really came to a conclusion, to a solution of this. Why does it do that? Why does it sort of go around this bend and then continue and never stop, sort of thing? Well, it does stop, but it becomes meaningless. After a while, the geometry becomes meaningless. And I think I have found the explanation for that. It's there, so that when you start the test, it's well, I can use colors. It's a white circle. That's the start. That's consolidation. And this is a simple, both simple and direct shear. And then, as you're familiar with, you go up this line here. Your normal stress is constant. You don't change that. You just change the shear. And as you change the shear, you move upwards, vertically. And you get to a point where you have the red circle. And the red circle now suggests that you are at failure, because it's touching a typical Moore-Coulomb failure line. And the direction of failure, though, you can determine that too. It's that dashed line there. But if you see up here a direction like that, it cannot fail there. It's impossible for two reasons. One is that it's trying to fail across the fibers. Another one is that it's physically impossible because it'll have to go right through the bottom. So it cannot do that. So we'll have to wait till it fails, and it can only fail when the failure surface approaches the horizontal, and that's the green circle. I don't have to point at it. The green circle and the green line there, the Moore-Coulomb line, in terms of these other materials I mentioned, at least for rockfill and clay, will be the same. The red and the green lines will be the same, but they're not in garbage, because it is fibrous, and therefore when you get the failure surface across the fibers, you can expect a higher strength than if you get parallel, and that would be the green line, and that's final failure, and the direction of failure is now horizontal. So that is the reason. The red circle then is that knee, is that bend. That's when you reach that, and from then on the sample wants to fail, but it cannot. So it's in a state of failure consistently from the red circle to the green. It's much more obvious in clay. I have to be a little bit critical here. I see so many strange hypotheses made and this one was a big. I've even named them. I shouldn't have done that, I guess. But here you have these two blocks, sort of. They're made like hay. They're using hay wire and bales. It's like they are bales, in fact. And what they're doing is they're applying a force with these two hydraulic jacks there on the left side, and that's what we should concentrate on, this figure here. So they're applying a load here, and there is the reaction there. And the net result of that is the usual one, namely this line, and it's not even that, it doesn't even have that discontinuity now. It just keeps going and going, and it will never stop. And that's what it says in that paper. No maximum was reached, and so therefore, of course, what people resort to is to use that point there, because that's the largest you have. But that's not failure at all. What happens, in my opinion, is that one down there. You push there, and then you push there, reaction there, and of course you have something maybe not quite as neat as that. Maybe it's bulging or something. But what you're doing is a lateral compression test, and you cannot expect any maximum. Another case here of somebody doing a tension test in very nice apparatus. There was absolutely nothing you could criticize about the apparatus. But here is another trend that I have discovered. The moment you start using tension tests, things are negative. And when things are negative, people do the strangest things. And so what's happened here is that first you have the red circles, and they are just the good old consolidation circles. Nothing mysterious about those. Then you get failure, as close to failure as you can get, and that's the white circles. And there is absolutely no doubt about that, because the white circles are made up of the two principal stresses. And so you have the major and minor, and you have, so it so happens that the minor is negative, and that's where the danger is, because then immediately, not just this author but many authors that I could refer to, then go for the green circles, and they suddenly consider the major principal stress to be zero, and it's anything but. Now they were just lucky in this case, because they were quoting the values, they were quoting for failure where the values, those values there, the minor principal stress. And it so happens that if you really start thinking in terms of soil mechanics here, or more column, you have these 34 or whatever the degrees there with different C values, and so that your failure values are there, and there, and it just so happens that the vertical, the ordinates there are practically equal to the abscissa here, but that's luck in this case. I ended up finally with a split ring, as I call it. It's a new apparatus that I designed and had built when I was doing some work with the fresh kilns. It just occurred to me then that we need the lateral stress, and the lateral stress is we don't have anything to measure that with. So this split ring is you're just looking down at it there, and it's hinged up there or over there, and here we have load cells, and the point is now that we let the thing try to split, and then we measure with the horizontal dial gauge, we measure how far it goes, and with a load cell what the horizontal load is, and hence we develop the lateral stress. And of course we can use this for K0, so we can measure K0 pretty accurately, and Ka as well. We can just let it go, and then when we let the ring go where it wants, we can even do an unconfined compression test, and in the process we can measure Poisson's ratio. So it developed into quite a little test, big test. It's as you can see, 2 feet or 600 millimeter diameter. In that, from this view here, half of it is taken away so that you can see both how dense it is again, and you can see that there are rollers there. These plates are split so that it's free to move. Everything was calibrated, and we got some rather interesting results with that. Typical compression numbers are 0.25. That applies to many types of landfill, but of course it varies between 0.1 and 0.6 or something like that, but 0.25 is fairly typical. So this is just a consolidation, but if you now look at it, take out a typical one here, you'll find that and I wish Bjerrum was alive, that he could see this, because if you ever looked at the typical Bjerrum material, this is it. Garbage. It does exactly what he postulated, what he predicted the material would do. That takes practically no time for its primary consolidation, and then after that it creeps and it develops a memory, and the good old garbage does in fact do that. This is a test, a real test where we waited and waited for weeks and so on, and we let it creep, and we have all these different you can go from B to C if you load it rapidly, just as postulated by Bjerrum, and then if you leave it at that stress, then it'll just creep down there, and of course we'll have to find now a relationship here. How does it creep? We need that law. Somehow we have to develop that. That's not developed here, and it doesn't have to be. The point is that it's going down, so it's going, say, from, if you want to end up at point D for David, you can go from B for bread to C quickly, or you can load it very slowly and go directly from B to D. There are various ways you can get to it, so that it's well defined in the stress strain space. Different contents of earth in the garbage mixture. There's always some mineral soil, always. You can't get rid of that. They use it for daily covers. They use it for everything. So then you can, if there's 100% soil content, you might have 0.03, and if you have no soil content at all, you can expect to get this 0.25. Interestingly, there is very little difference between 50 or so percent and 0% earth. And if you think about it, that's not surprising, because at 50%, you have the soil, in between the voids of the garbage, and the governing factor there is the governing behavior is that of the garbage, not that of the soil. K0, then some values here. The test numbers, of course, don't mean a thing to you, and they don't really to me either. I've forgotten what test numbers they were. What does mean something to you is that test on the right was more fibrous, significantly more fibrous than the test to the left, and hence, as expected, at least when we were getting to test number 5, we started to know the material, and as expected, the K0 value was smaller, was lower, with more fibers, so that there is a direct relationship between the fibers and the test results, K0, which we have plotted, of course, later. No, it's there right now. We need to spend just a few more seconds on this slide, maybe. First of all, you have the dashed curve, and that is a typical relationship that I told you about, that I suggested, that the higher the percentage of fibers, the lower is K0. And the red, the 5 points there, starting there, 1, 2, 3, 4, 5, are actual tests. And then I took the liberty of expanding the thing, or extrapolating it up here, because it would have to end up around 0.5 or so. If now we remove the fibers, we know, and now you can see how important it is to classify the stuff. The classification will tell you, will of course show you the fibers. What are fibers? Paper, plastic, wood, all elongated things, so that you can actually come up with a number. And that number typically is from there down to there. Here you just deduct the fibers, the percentage of fibers, and I was surprised when I got that result. It's quite consistent. So for all of these 5 materials, as you remove the fibers and go all the way back, and you know that number there, because that's a matter of classification. That's what we can get by simply classifying and weighing. Then of course we go vertically up there, and we find that they all are between 0.45 and 0.48 or something like that, which is what you would expect for a fairly loose mineral soil without any fibers in it. That would be of importance, of course, for prediction of the long-term behavior of this stuff, because you can expect one thing, and that is that this decomposable material will decompose. It will disappear. One interesting thing which is of interest to people who deal with earthquakes, but it doesn't have to be earthquakes. It can also be static. You measure a K0 value, in this case 0.4, and then you relieve the pressure on the split ring. So, and you measure, how you're trying to get Ka, which you get for a sand is very, very simple, which we did with the split ring, and it gave us what we expected, something like 0.3. But in this garbage stuff, it was reasonably fibrous. We just couldn't even reach it. Finally we reached 0. Went down from 0.4 and went down to 0. So that was one thing that we found out from that test. Another interesting thing we found was that if we reduce this very quickly, within seconds or maybe a minute or something, then it came right down to 0 right away, no problem at all, and stayed there, which ought to be of interest to earthquake engineers. And I'm not one, but I can feed this to them, that information. If you're not talking earthquakes, if you're talking long-term, then there's a third thing that we discovered from this test, and that is that particularly, let's look at the last one. It's most instructive. You get to here, and you have a very, very low K value now, practically 0, but not quite. And then you leave it. You go home, and you leave it over the weekend or something, and then you find that it has been growing. It's going back to its K0. And that, of course, is of some interest now to those of us who deal with stability, what this stuff is going to do. And this will require analyses where I'm not an expert. It will require it will require a full consideration of stress and strain. So we're into finite element treatments and all that, because we now have fairly good values for the stress-strain characteristics of garbage. If you do an unconfined compression test, it's incredible. The first one we did, which may have been this one, we reached 1400, and we stopped for one reason, and that was that the steel frame broke. It wasn't the sample. The sample wouldn't give up at all. We're learning about fibers. It's a compression test, and it's practically a consolidation test. And if this value there of 1400 kPa, you can multiply that by about 20, so you reach, you know, an extremely high stress. And in terms of horizontal, let's just jump right to the Poisson's ratio there. The Poisson ratio never exceeded much 0.11. The scale is on your right side. So it's nothing like elastic of 0.25 to 0.33 or something. It was about 0.1. It hardly expands at all, just 0.1. Again, of some importance in stability. And finally, we are now looking at settlement. We need to know something about that. This very simple curve is very expensive. It's the result of some 14, 15 years of field measurements of this big OII landfill near Los Angeles, which is about 80 meters, 275 feet or something thick. And so this is a window sort of thing. And now we have some idea of the first 15 years after construction. So the point 0 here, I call that EOC, end of construction. That's when the thing came up to its full height and when they were finished. How do we go on from there? We have to be careful. The normal so-called relationship used is that the settlement is proportional to the logarithm of time. And and that's the popular concept. And of course that concept is physically impossible, because if it carries on like that, the whole landfill is going to vanish and it'll end up as a hole in the ground. It just never stops. So that's impossible. So we have to introduce another equation. So this is a little bit unconventional. This is from my forebears, the Vikings, and we happen to have a whole lot of stuff, Viking stuff, which we can investigate, and it's there. It has not decomposed. It has decomposed partly, but not totally. We have these ships, and we have to realize then that it takes more than 1,000 years for it to decompose. Then I've been talking to archaeologists and chemical engineers, and we've come up with a maximum figure of time required for decomposition, and the figure I've come up with, the maximum is 10,000 years. Now we're getting back to glacial time, which is quite tidy. So all decomposition, and we should be able to find things almost back to the glacial time. But 1,000 years, we know that for sure. That we can look at today. So now we have that end point of say 1,000 to 10,000 years. We have another one which is fairly obvious when you think about it. That is that all of this stuff is going to decompose. Not all of it, not the minerals, but going back to the graduate student work there, we can determine the mineral content more or less exactly. And if the mineral content could be 40%, could be 50%, we know also that is going to be fairly loose. So we can say that we're going to be accurate enough by saying that the final porosity is going to be around 40%. So we have the left figure, and we have the right figure here. And so if we do some simple calculations, again, you don't have to study the stuff, but you can see probably that these are definitions. Mineral content is defined the same way as moisture content, and so on and so forth, to have the total volume, which we call 1 perhaps, and we end up with a final void ratio of that figure, the left figure that we looked at, and that means that so I'm sorry, void ratio, I'm saying that because well, we do that too, but when we prepared this PowerPoint thing, we couldn't use Greek letters for some reason, so we had to use these, and that says epsilon. Epsilon, F final strain is 63%. So we have that one. Then I went to the Department of Mathematics because my mathematics has become somewhat rusty over the years, and we developed that equation. And that equation gives us, we have that final point now, the porosity there, the final, I used a 0.6 there instead of 0.63, so it's in that same order of magnitude. So we have that. We have the 10,000 or 100,000 months or so, 120,000 months. And when you get up to those high figures, it's not really all that important whether it's 1,000 or 10,000 years, because the Viking era is about there. So that doesn't make a whole lot of difference. In 1,000 years, it'll decompose 90%. So we have a new curve, and I've started to use that relationship. And besides, I have no hesitation in telling people what's going to happen in the next 1,000 years, because I won't be there to check it anyway. You can develop several relationships. I'm getting to the very end here. You can the vertical distance between the parallel lines is that relationship that we just looked at by the mathematical expression there for settlement, and the white line is the end of construction of the entire landfill. So now we can start looking at what happens from now till whenever, and you go from the white curve on, and then you can calculate things. You can calculate this also in terms of dollars, because I was just working on a project in Delaware, I think it was, and they were using 10% settlement. And I told them that by the end of the construction they would be at closer to 30%, and apparently that represented millions of dollars of savings. So that this is not just academic. And I think finally we have, I found a reference. All those colored points and curves you see are field observations up to many years. They had quoted in days, so I didn't change the days. But these relationships now, depending on whether you use 1,000 years, which is 12,000 months, or 120,000 months, 10,000 years, you get these different curves, and you have to expect some range here, and so you can see now you don't have to look at all these weird relationships you hear about, that peat has primary and secondary and even tertiary. These are not geotechnical characteristics, they're mathematical. This one here actually fits very well, so far I have found nothing against using that relationship. And I just wanted to show you that it's sometimes of some importance to get the permeability of the material, and we have this 2.5 foot diameter where you put water in the middle, and then you measure the lateral. And if you're interested in the permeability of landfill, of garbage, it's somewhere in between 10 to the minus 5 and 10 to the minus 4 meters per second. And thank you.
These tests that you've developed, they're only in your laboratory, are they?
Yeah.
So if people want to run some tests like this, they've got to call you.
Yeah. Well, not necessarily. They did develop the consolidometer, a large one, and also the simple and direct shear for that OII, and they were done by Geosynthetic. I don't know where that apparatus is, but it apparently cost them about $500,000 to make it. It was very elegant. It was like this, but this is the prototype, and they were up to UNB to check that, and they made, mine is a Volkswagen and theirs is a Cadillac.
Do you have a feel or opinion of how the scale effects would be with the size of equipment, as if you're using large equipment for testing compared to conventional soil testing equipment, the scale testing is not related to conventional equipment with the soil size part.
Yes, did you say a feel for it, a feeling for it? That's all I have. I don't know. I have a little bit more than that, because we tested coarse material, and then we also took it apart, and we threw out some of the coarsest material and tested the finer portion and got the same results. But there's one other thing that struck me, that the results that I got are quite similar in many respects to peat. And peat is fine fibrous, and the fibers we're talking about are sort of 2 millimeters or 3, and they gave the same type of result. So my conclusion from that tentative conclusion is that the garbage will have to decompose pretty severely before you get a real change. And when you get down to that size, you're pretty close to a pure mineral soil anyway.
Would you be willing to give the estimation as to how this performance would stand up in a bioreactor landfill as opposed to a dry tomb landfill, where the liquid has been introduced over the course of life in landfill?
My impression after 20 years, but I have no real answer, I think, is that the voids, I did mention it before, the voids are so small that I don't really think it makes much difference if you have water or not. The water content is going to be very low. It's extremely dense. I'm not basing it only on a feel for it. This OII landfill, they were drilling 33-inch diameter bucket augers to no less than 150 feet. And the videos are very interesting. They had video camera down there. There is water dripping, but not a whole lot of it. It's about the same, it looks about the same density, and it looks very dense from the surface to 150 feet. And I don't think water is going to make too much difference.
I have a question. How can the voids be so small and yet the permeability high, and you're talking about strains of 63%?
Oh, yeah. When you have a strain of 63%, you won't get much more. That's when the voids are so very small, and the permeability tests that we did not have a 63%. That was a more porous material. It's a good question, but I think that's the right answer. It was not as dense as some of that material I showed you.
Any other questions? Yes, Nick.
Everybody else has done studies on this void ratio, or this void, this comparison between the voids and time. That's this equation that you came up with, find voids over a certain amount of time. Do you know anybody else has come up with an equation?
No, I think that's a new one.
This is the first time anybody's ever done that.
Yes. And I have covered a fair amount of literature. I haven't seen that at all, no. You either see settlement or void ratio, whatever, strain as is linear, is proportional to log time, or log strain linear or proportional to log time. That's the kind of thing you see. And in other instances, people, authors are just stating that we assume that it's going to be proportional to log of time, and we assume that all decomposition will be over in 25 years. You find all kinds of strange statements, and you have to sift through them. But I have never seen an equation like that one. It's not even the same as Lowe, Gibson and Lowe, I think it is, equation. So I will publish it. So it will be peer reviewed and then accepted or rejected.
Thank you, Dr. Landva, for an outstanding lecture. We have a certificate for you. I'll read it. It says, Certificate of Appreciation. We thank Professor Arvid O. Landva, University of New Brunswick, Fredericton, Canada, for delivering his lecture entitled Behavior Waste Fields at the occasion of 9th Spencer J. Buchanan Lecture, and it's signed by our department head and by myself.
Oh, thank you very much
Thank you
indeed.
very much.
Thank you.
My introduction of Professor Holtz is much more classical than my introduction of Professor Landva, mainly because Professor Holtz is the president of the ASCE Geo-Institute, so I don't want to take any liberties which might endanger my geo future. I'm just kidding, Bob. Bob is a good friend and a class act. It takes leadership, energy, and a good sense of politics to attain this prestigious position, and Professor Holtz certainly harbors these qualities and more. Professor Robert D. Holtz received his bachelor's degree and his master's science degree in civil engineering from the University of Minnesota in 1960 and 1962, respectively. After a special program in soil mechanics at Harvard University in 1966, he obtained a PhD degree from Northwestern University in 1970. He then worked as a research engineer at the Swedish Geotechnical Institute in Stockholm until 1973, at which time he joined the civil engineering faculty at Purdue University, where he became full professor in 1985. In 1988, he moved to the University of Washington in Seattle, where he's professor of civil engineering. He is the author, co-author, or editor of 21 books, mostly on geosynthetics and soil improvement. He is an active consultant with projects in France, Italy, and the USA. He has delivered the Kersten Lecture, the Cross Canada Lecture, and the Ardaman Lecture. He was the president of the North American Geosynthetics Society and is currently the president of the ASCE Geo-Institute. The title of his Buchanan Lecture is Geosynthetics for Soil Reinforcement. Please welcome Professor Robert Holtz.
Thank you very much, Jean-Louis, and good afternoon, ladies and gentlemen. It's a real honor and a pleasure for me to be able to present the 9th Buchanan Lecture. I never had the opportunity to meet Professor Buchanan, but I have a colleague that worked for him for a number of years, Joe Mahoney, who was a professor in my department. And so I asked Joe for some Spencer Buchanan stories. And before I tell you those, I got a phone call about 3 weeks ago from Mr. Bill Shannon, one of the founding partners of Shannon & Wilson, a premier geotechnical consultancy in Seattle. And Bill says, "Oh, I see you're going to be doing the Buchanan Lecture." And I said, "Yes." And he said, "Well, I knew Spencer Buchanan very well. We were close personal and professional friends." And I said, "Well, I have to hear about this. Let's go out to lunch because I want to get all the details correct." And so we went out to lunch and he started talking about this. Now, to give you a little background, Bill graduated from our department in 1936. That's before I was born. So, and in those days, we didn't have a graduate program there. And so the best and brightest of our graduates were sent to either Harvard or MIT. I guess it's an example of go east, young man. To either Harvard or MIT, and many of our really distinguished graduates in our profession that were graduates at the University of Washington distinguished themselves very well after that MIT or Harvard training. In Bill's case, being interested in soil mechanics, he went to Harvard. He graduated in '37 with a master's. He went to work for the Army Corps of Engineers in the New England District, building dams and other facilities. And at the start of the Second World War, was sent to Vicksburg, Mississippi. And if you've read the biography, you'll read that Spencer Buchanan was working at WES, Waterways Experiment Station, at that time. And Bill was down there, he said, for only about 6 months, but he became very good friends with Mr. Buchanan, even to the point that about 15 or 20 years later, they were building a large freeway project through the center of Seattle. And apparently this taxed the geotechnical capabilities of the profession in our area. And Spencer Buchanan and Associates sent a couple of drill rigs to Seattle, so there's even a real close Seattle connection. And Bill said, well, they didn't work out real well. The drillers weren't used to our hard glacial tills with all the rocks and stones, and he said, I think they lost some money on that job. But anyway, I said, were they interested in starting a business in Seattle? He said, oh, no, they were just up there to try to take advantage of this large construction project. And this brings me then to my colleague, Joe Mahoney, who is a graduate of this department. He, in fact, has all 3 of his degrees from A&M. Professor Litton was his major professor for his PhD. I said, Joe, you have to, I knew he had worked for Spencer Buchanan and Associates. I said, I need to have some stories to introduce this lecture. And he said, well, Bob, that man changed my life. Well, that's very strong words. I think somebody to say that. I said, well, you have to tell me now, explain. I don't know if you still have this, but apparently there was a 1-credit senior seminar course that everyone had to take. And Joe's last semester, he had Professor Buchanan, and at the end of the semester, Buchanan collared him and said, Joe, you've got to come to work for me for the summer. And Joe said, I'm sorry, I've got to go out to West Texas and finish my surveying summer camp, which you probably don't have anymore. I know we don't have that either. And so he said, I don't care, finish that, come and work for me. And Joe said at the end of that summer he was hooked. He loved working for Mr. Buchanan. He said the jobs, and this of course led to a long series of stories of consulting meetings and projects they worked on and all this sort of thing, which I don't have time to go into. Anyway, it's an honor for me to help to keep the memory of one of the giants and pioneers in our profession alive, and so I appreciate very much the opportunity. The other reason that I'm happy to be here is an opportunity to talk about geosynthetics, one of my favorite subjects. This, I believe, is another one of those developments in our field that is very close to revolutionary. The other big revolutionary development in civil engineering, of course, is the use of the digital computer. I mean, we can't imagine today, we were talking at lunch about slide rules, we can't imagine today what it's like to still be back in the slide rule era and try to function without computers. Now, to some extent, geosynthetics have not been quite as ubiquitous as computers in civil engineering. In fact, in structural engineering, I can't think of a use of geosynthetics. There very well could be one, but I can't think of one. However, in construction, hydraulics, environmental, in hard-side transportation engineering, and of course geotechnical, the use of geosynthetics has developed phenomenally, and the changes in the way certain problems are solved, I think, is nothing short of revolutionary in terms of those developments. The example I'm going to give you today, or the examples I'm going to show you having to do with soil reinforcement, I think are very good examples of that. But let me give you another one, and it'll follow up on our previous talk on municipal solid waste landfills or garbage dumps. Let's go back about 15, 20 years, and if you were charged with the design of a municipal solid waste landfill, and you would go through the presentation perhaps to the client or the regulators, and you suggested, oh, and by the way, let's try to use some of those new plastic sheets in there to augment the leachate collection and so on, you'd probably be considered a little bit crazy. Today, if you had that same project and did not consider geomembrane liners, leachate collection systems with a whole host of geosynthetics, you would be considered hopelessly out of date and probably be advised to maybe get some help on the job and let's do it the modern way. And I'm talking about in 15 or 20 years. I think that's quite remarkable, such a development so rapidly in civil engineering. And the other examples that I want to show you today having to do with soil reinforcement are equally, I think, equally revolutionary. The other reason that I love soil reinforcement is because it combines the best of geosynthetics. I said that it's a favorite topic, but also geotechnical engineering. You really are involved in bearing capacity and earth pressures and slope stability, all the nuts and bolts stuff of geotechnical engineering and soil mechanics. And so that's one of the reasons that I find these developments so exciting. Now, what I thought I would do today is to kind of introduce geosynthetics. I know that there are some of you that have had considerable experience with this, and so I'm hoping this won't be too redundant. But to present kind of an overview, an introduction to these materials. In the paper is a lot more detail, a lot more discussion, as well as some references on this introductory material that I hope if you need additional information that it'll be available for you. And then we will get into the three big applications of soil reinforcing: embankments on soft foundations, steep slopes, and retaining structures. Well, I have to show you this. Gary Larson's one of my neighbors. Actually, he lives around on the other side of the neighborhood, a big house on the lake. And a few years ago, I saw this slide. I thought, well, that's a little bit silly, but after the geo-environmental movement got started, it starts to make some sense. I also want to then show you this. My daughter went to Glasgow University. She graduated several years ago in Scotland, and they're boring sea civil engineers. I tore this out of her telephone directory in her flat because I was so intrigued by that. Now, it turns out that's gotten a lot of notoriety, and the Institution of Civil Engineers has complained to the people that produce the yellow pages, and so now it says something like sea drilling contractors or something much more boring. But anyway, this is an aerial view of our campus, the downtown of Seattle, the Space Needle from the 1962 World's Fair. And if you come to Seattle, this building right here, that's my office, right there. And I want to show you a photograph showing that fountain there. That's Mount Rainier in the background, which is supposed to be an extinct volcano, but we're not really sure. It's dormant, I guess would probably be a better word, which is about 4,400 meters or a little over 14,000 feet. About 3 days a year we're able to see the mountain. It's quite an event. It stops raining. If you go to the ASTM standard D4439, you'll see geosynthetic defined. A planar product manufactured from a polymeric material, that's where the synthetic part comes in, used in some kind of geotechnical material, soil, rock, etc., as part of a civil engineering project. And it's a fairly general definition, but it says all the key words. You notice planar product, so it's in sheets or strips or something like that, and used with a geotechnical material in some kind of a project. This slide lists some of the common geosynthetics. Geotextiles were the first ones that came on the market about 30 years ago. Geomembranes were those plastic sheets that we use in municipal solid waste landfills. Geogrids, geonets are used as drainage products. You can combine these materials to make a geocomposite. Professor Kerner talks about geopipe. He probably mentioned that in his when he gave the Terzaghi lecture here. And then if you're from my neck of the woods, in fact at the Brio party, I'll tell you after a couple of glasses of wine what a geoduck is. There are a lot of products. When I first started playing with these materials in the early 70s, there might have been 5 or 6 of them. Today there probably are 600 manufactured in the world of grids and nets and composites and all sorts of different kinds of fabrics and textiles and so on. The range of products that are available is really phenomenal. And this is a benefit as well as a little bit of a problem. In the earlier days, you had 1 or 2 products that you would use and that was it. If it worked, great. If it didn't, you didn't try it again. Today, you've got all of these products available, and this gives you a tremendous selection of products that probably there's something out there that will solve your problem. And that's a tremendous benefit, I think, to the engineer. The polymers that are common are polypropylene, polyester, and polyethylene. Polypropylene, the black plastic that goes into garbage bags, is an example of that polymer. It's a really inexpensive polymer. Polyester, my trousers are made of polyester. It's a very common material in synthetic polymers for textiles, such as clothing. Polyethylene is used for sheets, for example, in the geomembranes. It's a very common geomembrane material, as well as pipe and some geogrids. That's the great bulk of all the geosynthetics are those 3 polymers. This slide discusses the function, and this is elaborated on a lot more in the paper. Geogrids are used essentially only for reinforcement. Reinforcement, separation, cushioning, filtration, and transmission geotextiles perform that function. Geonets and geocomposites are used primarily for transmission, for drainage products where the plane of the product is used to carry the liquid, leachate in the case of the landfill, drainage materials in case of an edge drain on a pavement, and so on. And then geomembranes are used for isolating, to keep that leachate out of the environment. This slide lists the applications the primary applications of geosynthetics. Drainage and filtration, erosion control, that's the hydraulic side of the business, and also in environmental, those functions. Roads and railroads, that's the hard side of transportation. The reinforcing, I've mentioned embankments, slopes, and walls. Those are what we'll speak about the rest of the time today. And then in waste containment, there are a whole myriad of applications for geosynthetics. We don't have time, obviously, to go into the details of those, but in the references I've given you, you can follow up on that. Can you design with geosynthetics? Yes, you can. Today we have design procedures, we have properties, we have all of the things that we need to approach design of geosynthetics like you do any other civil engineering material. You can do this from a generic point of view. You can select products generically. You can write specifications. You can do design in the same way that you design with steel or concrete or soil, timber, or any other civil engineering material. Same approach. We don't want to do this for design. How do you select your geosynthetic? You throw a dartboard, and if it hits, that's the right one, or the properties values. This was kind of the way it was done in the old days. It was kind of a catch as catch can, whatever you might hit. And if it passed, that's great. This is the other, I think what a lot of engineers have done in the past is you just kind of say, it's too complicated, I'm just going to pick one and hope it works. Don't do that. The properties, and this is one of the things that's really developed in the last 15 or 20 years, is the ASTM has been extremely active in developing test standards, materials test standards, for properties that we need for design, the strength, the friction, all the other characteristics, the opening size for design, for permeability, et cetera, et cetera. And then, much as we do with a lot of, certainly structural materials or foundation materials, you have the constructability or the survivability properties, a whole host of properties that relate to the ability of the geosynthetic to survive the construction operations. Many of those are index properties, where they don't give you the real strength, but they give you an indication of the strength sufficient to be able to select a product that will survive the construction. And then the third case is the durability. Now we've seen 10,000, 100,000 design lives today for garbage. Well, the same thing's true for geosynthetics. How long are they going to last? Say, well, they haven't been around. They've only been around 30 years. How do we know they're going to last 500 or 1,000 years? Well, the Federal Highway has spent quite a bit of money the last few years, and a number of states kicked in on this also, with a study on durability of geosynthetics, a geosynthetic polymer. Worked with polymer chemists, did some accelerated aging tests, and the bottom line is that in most geotechnical soil situations where we're going to be using these products, the half-life of their, with respect to strength and other properties, is between 500 and 5,000 years. Like Professor Landva says, he doesn't worry about things that far in advance. You shouldn't either. You don't have to worry. So you have factor of safety of 2 in 500 years. Worst case, it'll be down to what you really need for stability, for example. So I don't think we have to worry anymore about durability of these products. Now, if you have a special case, you have a chemical waste dump, or you're using your geosynthetic in an area where you're not real sure, well, you're going to have to take some samples. You're going to have to find out what that chemical is. You can go to the manufacturers. They have very good data on the impact or the influence of certain chemicals on their polymers, and they can tell you whether it's going to survive. And there are a number of other cases that you can do. So if you get out into a situation that you don't know, there are things you can do. We've not found any bugs that like geosynthetics. There are some bacteria that eat oil that have been used for oil spill cleanups. And since these are basically products of the petrochemical industry, polymers are made from oil, I don't know if there's some bacteria that will eat these geosynthetics, but we've not found that so far. Rodents could be a problem. ASTM has worked for many years on the rodent test. They have a standard 1 liter jar. You attach the geosynthetic here and you put a rodent of the opposite sex or some food or something here. And if the rodent eats a hole through it, of course the product fails. If the rodent starves to death, it passes. And they have been trying for about 15 years to find a standard rodent. They've tried lawyers, but they keep starving to death, so it doesn't work very well. So now when you get down, you're doing your design, you're going to select geosynthetic. If you do not see improved performance or you don't save some money, you don't need a geosynthetic. One of the nice things about most geosynthetic designs is there's an alternate, the traditional solution. You can use a graded granular filter instead of a geotextile filter. If it's cheaper, you can get it in better, it'll perform better, use it. You don't need to use a geosynthetic. The geosynthetic solutions a lot of times are cheaper and better, and that's of course why their popularity has increased so much in the last few years. And the other thing is that you can use this as a design alternate for the contractor. If you have a design with and without, that can help you just check and make sure your calculations are correct. If you're getting the same kinds of numbers for both designs, gives you a lot of confidence as a designer, and you get a construction alternate for the contractor to make the choice. So there's a lot of advantages in that regard. But remember that you don't want to just use a geosynthetic just because the guy in the next cubicle is using a geosynthetic on his design. Don't just use it for yours without thinking about it. And make sure that you see improved performance and cost savings. As I mentioned in the paper are a lot of additional references on some of this background material, and if you would like additional information, I think that'll guide you towards those references for additional information. Let's get into soil reinforcement. Not a particularly new development. This is a ziggurat from ancient Mesopotamia, which is a modern day Iraq is that part of the world. And this ziggurat, or a temple, which was built about 3,000 years ago. You see these horizontal lines, and Professor Carrizel in the 1985 Soil Mechanics Conference in San Francisco showed this photograph where they had excavated some of these woven reed mats that were used to reinforce that structure. Now those priests that built these ziggurats 3,000 years ago, I don't know what their design life was, but it was probably a little more than 100 or 1,000 years. And certainly the fact that they've lasted 3,000 years with a highly biodegradable material should give you some confidence that these modern engineered products, even though they're made of a polymer, you have some confidence that they're going to last. Corduroy, used in construction of roads in the colonial times. This happens to be from upstate New York. Unfortunately, I cut the date off up there, but it was 1927. But that's an example of reinforcing at the base of an embankment. Bamboo fascines are used in Southeast Asia. This is a highway job near Bangkok, where they laid the bamboo stalks perpendicular or transverse to the center line of the road. There's about a 5-foot high embankment here for supporting that roadway on very, very soft foundations. And a modern day version, this is a geosynthetic reinforced embankment, Mobile Harbor, Alabama. Was built by the Army Corps of Engineers as a dredged retention dike. They dredged Mobile Harbor, pumped the dredgings into this retention dike. This is built on material, it's a 25-foot high embankment built on material 60 PSF, about 3 kPa. You cannot walk on 60 PSF stuff. You'll sink in up to your armpits in that. There were very high-strength woven geotextiles used and very special construction procedures used to construct that embankment. It is possible to do. Here's a steep slope. I think that tree is vertical. This slope is standing at a much higher angle of repose than 30, 35, 40 degrees, or whatever compacted clay. I don't know what the embankment material is, but by using geosynthetics reinforcement, a very steep embankment slope can be built, and we'll talk about that, and retaining structures. This happens to be a wrap face, geotextile wall, but you can build rather impressive abutments and structures out of geotextiles and geogrids. And I'll show you some examples of those. So let's start with the reinforced embankment on soft foundations example. This is the case of where you've got to build something on a soft site. And you go out to start the construction, and it's a soft site. You've got problems. And you probably have some of those around here. I know we certainly do in the state of Washington. And this is one way that we used to. I worked on the Highway Department in Minnesota. This is the way we built fills. It was called the displacement method. You just keep dumping sand until it finally stabilized, and you hoped everything was okay. In this case, they've gotten a failure. This is where the toe of a slide here, and you can see one here. This is a Corps of Engineers job, so they had plenty of money. You can see how much sand they moved. You and I would never get a permit to be able to encroach on that waterway, but since they issue the permits, they're able to get away with it. Now, when you start to look at this problem, how are you going to do it conventionally? I've got a list. In fact, I have 2 slides of conventional solutions. You take a basic foundation engineering course, or you're getting into stabilization of embankments on ultra-soft foundations. You've got a number of possibilities. In fact, I think there are about 9 or 10 different possibilities. One is you can build a bridge. Our structural colleagues like this one. That's one solution, and we call it elevated structure. It's really a bridge. And you can use regular structural materials on that. You can use berms or flatter slopes, depending on the height of the embankment and how soft it is, just to weight the potential slip surface down and make a wider embankment so that it's more stable. Lightweight fill is used in some cases. Embankment piles, we were talking about that this morning with some of the students. When you have limited depth to firm bottom, you can use embankment piles. You can't in Mobile Harbor because the rock is, 5,000 feet or something like that. Excavation and displacement or replacement with high-quality graded granular fill, high-quality granular material is what's shown on that previous slide, where we're going to either you make an excavation and replace it with high-quality fill, or in this case, they just displaced it. So that's another possibility. Preload and surcharge with or without vertical drains. That's another way to do it. I put in chemical and electrical. If you start to look through the literature, you always find one case somewhere in the world where somebody managed to use electroosmosis or chemical treatment or something for a soft ground embankment project. Vibral replacement, stone columns, sand columns, cement columns, deep soil mixing, that's another possibility. And finally, reinforcement. Now here's another example of how rapidly the developments have occurred in this case. About 5 years ago, I got a textbook written by 2 Canadians, Francois Tavenat and Serge Leurier, and a French colleague of theirs, Jean-Pierre Mognan, wrote a book on embankments on soft foundations. And it was published in French in 1985. About 1995, there was an English translation. I got it out. They had 1 paragraph in this whole book on reinforcement. And they said what most of us would have said 15 years ago, it's kind of experimental. It's kind of unusual. Maybe only in special cases would you use a reinforcement. And today, if you have a soft ground embankment job and you don't include reinforcement in your list of possible alternatives, you're not doing your job. I think we understand how they behave. We know how to design them. I'll outline that very briefly. We know how to select materials. We know how to get the test properties. And we know how to construct them. And so there's almost no excuse for, I think you should consider all these other methods also. But definitely you should include reinforcement in this list. Here's an example of another dredge spoil dike. This is at Newport News, Virginia. The Craney Island. It's another dredge disposal retention site for the Corps of Engineers. You see them placing sand on geosynthetics on dredge disposal material out here that you can't walk on. On this slide lists the design. These are ultimate limit states, so they are the limits that we look at for design of reinforced embankments. You have to do all of these because these are possibilities for failure, the ultimate limit state that we have learned from case histories and from observations of others. You know, failures are useful as long as they're the other person's and not yours. We've learned a lot, and fortunately federal agencies like the Corps of Engineers, states have been willing to tell us or describe some of their failures. We've learned a lot from them. And for example, we have to have overall stability, overall bearing capacity of that foundation, or it's just not going to work. It's possible, depending on the soil profile, that the soft clay can extrude out from underneath the embankment. And that's another design that we make sure that the conditions are strong enough for our particular embankment that doesn't happen. We can get a rotational stability problem, or really kind of a classical slope stability type problem, and so we check that to make sure it's okay. The reinforcement, of course, goes at the base of the embankment, and we add that in as a restoring moment to make sure we have adequate factor of safety. We can also have lateral spreading or lateral sliding of the embankment, and we check that. And then if you had a very high embankment, you might have a slope problem in the embankment itself. We check all of those just to make sure we're okay. And then we also have to consider the serviceability limit state, in other words, the performance of the embankment, depending on how much, what the facility is, what kind of settlements we can tolerate. And so we do a foundation settlement, just a classical Terzaghi settlement analysis using Terzaghi theory, and we also could worry about, or we should worry about, whether the reinforcement stretches, and so the modulus of the reinforcement must be sufficient so we don't get so much stretch at the base of the foundation that the embankment settles and it's considered to have failed, even though it didn't fail in instability. The procedures for those design limit states are very well established. In fact, many of them, like the bearing capacity one and the settlement analysis, are classical soil mechanics that everyone knows how to do. The geosynthetics that are used for embankments on soft foundations include geotextiles, geogrids, and then strip drains are used, of course, for accelerating the consolidation. And I put those in the list because they are a geosynthetic, a geocomposite. Construction is absolutely essential that you build it right or it's not going to work. So construction is very, very important in these kinds of ultra-soft foundation construction projects. You have to have the right equipment. You can't use regular highway construction equipment. These are wide track dozers, light equipment, and so on are required. Site preparation, don't remove the metal mat or the root mat. You always leave that because that gives you a little extra reinforcement, a little extra insurance. How you place the geosynthetic, and that includes sewing and seaming, and there's a whole host of things that are involved in that I don't have time to go into, but again, in the paper, they're described or at least outlined, and in the references there's sufficient detail to tell you how to do that. And then how you place the fill on extremely soft ground or on a little bit firmer ground. Typically, the sheets of geosynthetics go toe-to-toe across the transverse length or width, of the embankment. There's the center line. And then you construct in kind of a U-shaped leading edge to make sure, dump the material off here on already placed material, and then it's spread to be able to maintain the geosynthetic in tension, and that helps stretch the fabric. You have to seam or sew these sheets, of course, before you place the fill, so that work will all have to be done up here. There's a lot of details associated with that we don't have time to go into. The next topic is slopes, reinforced slopes. We're talking about steep slopes. Here's one that's pretty steep. You can see from this guy standing here that it's also fairly high. And being able to build a slope at an angle greater than the angle of repose or the safe angle for a compacted clay, the only thing you can do is to reinforce it, and geosynthetics provide an opportunity for doing that. Shown here on this cross section are some of the features of geosynthetic reinforcement. The strips, primary strips going back into the backfill, and then depending on the spacing of the main reinforcement or the primary reinforcement, you may require secondary reinforcement at the face. Sometimes these are wrapped around on the face of the reinforcement, face of the slope. Sometimes they just go right out there and terminate. The situation is such that you have that what's happening at the face is very local. And so you may need to do something at the face just to retain the fill right at the face. And so the wrapped face geogrid or geotextile is very appropriate for that. What's the purpose of the reinforcement? Well, it's to increase stability, to provide a factor of safety that's greater than 1. And that permits you to steepen the slope over the angle that it would ordinarily stand at. And then there's been some work by having the geosynthetic right at the edge of the embankment. It gives the roller something to push against and is what we might call a compaction aid. And that's shown here. It's not a very heavy dozer, as you can see, but here the face is totally gone. And yet it's stable. And the reason is, of course, it's raveling a little here and running here, but the reason is that the earth pressures tending to cause that to slide are rather modest right at the face of the embankment. And this dozer now is able to compact that fill very, very well right close to the edge of the embankment, and it increases the stability of this material a lot. Here's a case history of an embankment reinforcement job, or a slope reinforcement job, I should mention, that occurred in one of the very early days using the geogrids. This is in southern Ontario in Canada. Clearly was a railroad failure, a slip out, as you can see. And one of the real advantages of using geosynthetics for slopes, and especially landslide repair, is that you can reuse the debris, the landslide debris, for the reinstatement of the slide. That means you don't have to haul the old stuff away and bring in selected material, but you can use the material that's right there on site. It just happens to be at the bottom of the hill. And just to show you how that goes in here, the sheets of geosynthetics coming in, and they're building this slope up. It's a steep slope, you can tell there. Here's a ladder that the guys use to walk up and down the slope. They have to have this fellow stand down here, lie down here to hold the ladder up. It's so steep. And I think this took about 3 days from start to finish by the time they got the ballast and the track reinstated. That fellow's still there holding that ladder up. Very efficient. Here is a slope that was built in northern Idaho on Highway 93, US 93, up in the Panhandle a few years ago with a wrap-face geotextile slope. They wanted to widen the road because of aesthetic reasons and so on. If you'd widen the road and bring the slope down, this thing would have been way the heck out there and an ugly scar. And so by using wrap-face geotextile for very substantial slope, we were able to widen the road and improve its traffic conditions. And here's a 35-meter high reinforced slope from Taiwan for housing development. You can see the truck up there. Here's the geogrids that were used. And because of the apertures in the geogrid, and of course in a warm, wet climate, the vegetation has reestablished itself very rapidly, and in a very few years you won't even know that that's a reinforced slope. It's a very good development because of that. Now I have to mention that there are a lot of computer programs out there. And I got this cartoon from a British magazine, Ground Engineering, and here are these two guys working with that little toaster that sits on your desk. If we can incorporate boundary elements rather than simple finite elephants, enhance the statistical evaluation of parameter generation, and stick with the fuzzy sets, I am confident that accuracy will be increased to at least the 4th decimal. And then here are the guys in the field doing the sampling. Put another shovel in, Pat. It's full cores they're wanting. And you can imagine, we want our full tubes, and so we got to make sure that they're filled up. And so if you're tempted to use these computer programs, especially the ones you get free from the manufacturers, caveat emptor, remember that. Texol was an invention of a continuous fiber filament reinforcement developed in France a few years ago. This was in our lab. I had a 6-inch diameter tube full of Texol that was shipped to me from France, and we just lifted the tube off of the pan, and the sand ran out. But I think you can tell there's a regular angle of repose, and there's what it is with the fibers. And you don't have to use continuous filaments. You can use geosynthetic short fibers. There are just lots of mini grids. There are a lot of things that can be used for reinstatement of slopes. This is the system that they have in France, the Texal system. And you can see their brand there. Basically what this is a shotcrete machine with a couple of spools of fibers, filaments, continuous filaments here. High pressure water and sand go out. They don't put the cement in the shotcrete. And the fibers in this thing is just developed back and forth and build this thing up on a slope, fairly substantial slope. This guy driving around here in the French Alps doesn't even know that that's geosynthetic. And again, the vegetation, if you're in the right climate where the vegetation can reestablish itself, you get a beautiful slope system. And now somebody needs to change my tray so we can finish up with the reinforced walls. This is the third area that geosynthetics have really had a tremendous impact for a reason that I'll show you in a minute. Reinforced retaining walls and abutments really basically started with the reinforced earth concept that was developed by Henri Vidal in the mid-60s in France. Terre Armée or reinforced earth. You see the components here. I'm sure many of you, if you drive the freeways in Texas, you see a lot of different systems, and many of them are the reinforced system with some kind of precast concrete face panel, backfill, and metal strips or sheets or bar mats or something going in behind the fill to provide the reinforcement. We can use steel reinforcement for walls, or we can use geosynthetics. Now, this is the very first geosynthetic wall that was built in this country. It was built in 1974 in southern Oregon in a national forest. Wrap-faced wall, about 6 feet high, as you can see. It's not very pretty, but out in the woods, just a few log truck drivers and some bear and deer that get to look at it, so they don't really care. You're going to have to cover the face because this now is exposed to ultraviolet light and subject to deterioration. So a lot of times we use shotcrete. This happened to be a test that was done in Colorado a few years ago, Glenwood Canyon. A 15-foot high wall, shotcrete for ultraviolet protection, and a surcharge it was a test to try to see if they could get the thing to move, and it didn't move. And one reason is you got to make measurements during construction or you'll never be able to see them. This shows why reinforced walls systems have been so popular. We usually look at cost of walls based on a face foot or a face square foot or a face square meter. I've got it dollars per meter here, height of the wall in feet or meters, and dollars per square foot over there. And these are all the conventional systems, bin walls, gabions, concrete cantilever walls, and so on. And you can see after about 30 or 35 feet, there's no competition. Structural retaining walls are just too expensive. I don't care what system it is. And here's reinforced earth, VSL, which are the steel, double wall, geosynthetic walls. All of them come down in this range here, depending on what you do for the face treatment. Geosynthetic walls without significant face treatment will sit down in this range right in here, $10 to $15, $16 a square foot. The Washington State Department of Transportation built a retaining wall, I'll show you in a minute, which was 40 feet high in Seattle. It was a temporary wall, so they didn't spend any money on the face. 40 feet, and it was sitting about right here, about $160 per square meter, $16 a square foot. But again, with no face treatment. How do you design? Well, this should look familiar to anybody ever designed a retaining wall. It's the same failure modes that we have for conventional walls. We make sure they don't slide, that they don't overturn, that the bearing capacity is adequate, and that the overall slope stability is adequate. And if it is, that's standard design procedure that you have for any retaining structure. Now, the internal design is a little different, but it's not that hard. What you have to do is make sure that the earth pressures don't exert so much force that you rupture the geosynthetic. In other words, that it has sufficient tensile strength to withstand the earth pressures. If you're having a face element on the front like the reinforced earth or some of the other systems I'll show you in a minute, you have to make sure that the connection strength at the face is adequate. And I guess the other failure mode is the whole thing can slide and the reinforcement can pull out of the backfill. And so we design for pull out. There are procedures available for these. They're very conservative and they work very well, very easy to do. Don't forget drainage. It's amazing how many failures have occurred of reinforced walls recently, and almost every one of them, water is involved. Now, it's one of those things that geotechnical engineers say, of course, so what's new? But unfortunately, geotechnical engineers were involved in those projects and they forgot some of the basic rules. Now, these are not new slides. You know where I got these? I got these out of Terzagi's Theoretical Soil Mechanics, 1943. So this is not new stuff. You know, we've got to remember, I guess we keep learning the same lessons over and over again. I don't know what. Anyway, don't forget the drainage. Material properties, the soils, the geosynthetic properties for the geosynthetic reinforcement, and the soils and soil mechanics. That's nothing. Everybody in the room knows about that. Geosynthetic reinforcement, the two properties you need are tensile strength and the soil reinforcement interaction parameters, basically the soil geosynthetic friction. This is that 40-foot high retaining walls built near downtown Seattle a few years ago. 40 feet, 20-foot surcharge. It was fairly heavily instrumented, and based on that, we got a lot of research money from the DOT to try to find out why the darn thing works so well. I'll just show you a little bit of the data. It was heavily instrumented. 40 feet high, recognize, or this is in metric, 12 meters. Here is the deformations or deflections of the face when it was 6 meters high and at a 0.6 meters high, and when the wall was completed and 9 months later. So that shows you how much creep you're getting. This was with a very low design factor of safety. It was temporary wall, so it didn't have a real high factor of safety. You will not see 120 millimeters in 12 meters. In feet and inches, that's, what is that? 5 inches in 40 feet. You'll never see it. You can't see that deflection. And what it points out is you've got to make that measurement during construction. If we waited until the end, we'd never see any deflection. You say, oh, the darn things don't move. Of course they don't move because you have to make the measurements during construction. I want to show you a couple of other slides. This is another interstate in suburban Seattle, Interstate 405. There's a temporary off-ramp during some construction operations. This is a fabric-wrapped geotextile wall. And I don't think you can put your hand between this wall, the temporary wall with the geotextiles, and this 3-lane freeway here carrying, I don't know, 6,000 cars an hour or something like that. Now, the guy that designed that other wall designed this one, works for the highway department. At that time, he was not the chief geotechnical engineer. Today he is. He has confidence in his design procedures. Can you imagine what that young man would be doing if this wall had moved out and had hit that bridge and they'd had to close the road? He'd be breaking rocks at Walla Walla or something like that. That's our state prison in Washington. So obviously the design procedures are conservative and he's got a lot of confidence in that. Let's talk about the facing treatments and finish up here in the next 4 or 5 minutes. This cartoon shows the ways that we treat the face of a wall. Retaining walls are ugly, and anything we can do to make them less ugly is an advantage. We can have full height prop panels here where you have to prop it or support it during the construction as you lay in the geosynthetics and the backfill, then remove the strut or the panel prop, and the thing should stay there, you hope, if you've done it correctly. You can have incremental panel or modular block panels, which are as you construct the backfill, you bring the face up. Wraparound facing, the 2 examples I showed you recently. And you could have a facade where you have large settlements or anticipate large movements, let those occur, and then come in later and put a facade, a false front on there, which can have your architectural treatment and that sort of thing. And I'll show you a few examples of those. Well, I forgot I had this one in here. This is at Glenwood Canyon, Colorado, if you don't shotcrete the face. Now, in all fairness, they're up about 6,700 feet elevation. The UV is quite strong. So here's the shotcrete part. This was left not shotcreted because they wanted to make the excavation and retrieve some samples. But you can see that within about 1 construction season, That's what happened. I mean, it's pretty ugly. But notice, it did not fall down. It did not collapse. So structural collapse, you don't have to worry about with these materials. They're very flexible, very forgiving materials. And in fact, if you go in on where these sheets are, a few sand grains, that geotextile is as good as new. Why? Because it's not exposed to ultraviolet. In fact, I can show you another slide, which is a side view of that test pit that was taken about 10 years after. So it's gone through 9 or 10 winters, freeze thaw. You're up in the Rockies, you can imagine what it's gone through. And here you can see the geosynthetics coming in. Here's another sheet, wraps around the face. And they're standing on almost a 90-degree slope. How come it hasn't collapsed with the granular backfill? Well, there's a little silt in there. There's probably some capillarity that holds that, gives it some apparent cohesion. It's quite remarkable. Didn't collapse. I should think as a designer, this is one of the greatest advantages you can ever think of in a structural system, that it's not going to fall down on you. You may lose the face and you'll have to repair it. Or it may look like heck with something like this, but it won't collapse. It's really quite remarkable. So you do have to shotcrete this. This is in Glenwood Canyon. The guy's shotcreting. Be careful. You don't want to upset the contractor in these jobs because, or always stand behind the shotcreter. I guess that's the thing. Here's some full height panels that Colorado DOT has experimented with the colored cement. These are full height prop panels, but you get the idea of something making them a little less ugly. It's really not too bad. Blends in with the soil, as you can see. Here is a welded wire wall, which is another reinforcing system in Olympia, Washington, which obviously a wet maritime climate. And within a very few years, all the vines have reestablished, and this hill or slope wall is essentially hidden from the public. The modular block walls that are very popular nowadays, and indicated on this slide why they're so popular. You can do different shapes and elevations and so on that would be extremely difficult to do in cast-in-place concrete. And so you can have vegetation growing here, all sorts of different things, a lot of flexibility in design and construction. In the Rocky Mountains, a friend of mine has built a number of little walls. This one is just with blocks of rock that they found on site and geosynthetics going back in, again to repair a landslide. Here's some more that he's done where he leaves the rock outcrops and then just use concrete blocks, regular blocks that you build houses out of. Here's another one where he's got the rubble wall here with different colored blocks to kind of make it a little more aesthetic, a little less ugly. He's done some tests. This is a reinforced with a very lightweight non-woven geotextile and modular blocks with the load test. And jacks up here, and they're putting all this load on there as a test. And this is my favorite, Bob Barrett. I'll give him credit for it. That's him right there. This is his wall right here. You see this reinforced wall? These are bed sheets from Kmart. I kid you not. He went down to Kmart and he bought these bed sheets and built this mound, if you will, this wall, and stacked up these jersey barriers, and the thing hasn't fallen down. And notice a couple of other things. The face is gone down here. Now, I don't know if I would stand there. I certainly wouldn't lean on it like he's doing. And I think I'd put my hard hat on and my steel-toed shoes, or I guess it's okay if he pushes it over that way, but isn't that remarkable? With bed sheets from Kmart. It's really quite remarkable, the things you can do. And now he also has a reverse batter wall, which I thought was fun. I think this, you can see the concrete blocks here, and built that up with an overhang on it. In fact, he's built these with the overhang of about 2.5 blocks out. So he's talking about 80-degree overhang. It's really quite remarkable. Research needs, I think in view of the time, let's pass on this. I wanted to show you that research is important because this is a 1999 earthquake in Taiwan, and here's a failure of a modular block-faced wall. The wall, again, didn't fall down, but the face fell off. I think that all these technologies that I'm showing you on soil reinforcing have a great future. I think they're going to revolutionize how we do practice for all of these technologies. I think especially for retaining structures because of cost. You saw the cost figures. They're so much cheaper. And we found out from studies and behavior during earthquakes that they're very flexible and very forgiving structures. Also, you save a lot of money. You don't need to have a lot of fancy foundations, expensive foundations, because they are so flexible and tolerant of differential settlement. So they have a great future in that regard. Let me finish up with showing you a frog wall. A friend of mine is actually an Austrian, but he's married to a Swede and lives in Sweden. He goes down to Vienna to see his mother, and he's driving along the road in rural Germany, and he saw this thing here, and he, what the heck? And he went to the local community, of course, speaking German, and asked them what's going on, and they said, well, that's a frog wall. If you don't believe it, here's a sign. And he said, what's going on? And he said, well, the poor frogs, they go across the road there, and they get squished, and it's a traffic hazard. And so we put this wall to prevent them from crossing the road and getting killed. And he said, you got to be kidding. That thing there keeps the frogs from jumping. He couldn't believe that. You know, clearly frogs can jump higher than that. He said, well, you know, they only cross the road during the mating season, and they carry the females on the back. The males carry the females on the back, and they can't jump very high. So I guess that's a good example of German efficiency. Somebody's gone out and measured how high they jump and built a fence just high enough. Thank you very much.
Yes, question or discussion period. Who's got a question? Okay, you go first.
So all the success we got, all the design methods we have, and all the testing and data we got, the state and federal DOTs continue to be reluctant to use the geosynthetic as well. You see that change in the near future?
Yeah, I think they've changed a lot. I know in our state, this is almost the first wall they choose that they look at. But that a lot has to do with the culture of the state and the experience and so on. But they find that they save so much money. Washington's not near as rich a state as Texas, and so they have to look around for ways to save money. And they found that as far as retaining structures are concerned, that they're so much cheaper that they consider a reinforced system almost from the beginning. And certainly it's considered as a design alternate to the conventional structural walls. And, but you're not, I mean, that's a very good question, because there are some states where they don't use them. And some states have very restrictive rules and code requirements and so on that almost preclude their use. And some states, I don't know, maybe they're biased or they had bad experience in the early days. I don't know why, but things are getting better, I'll tell you. Things are getting a lot better. And eventually money will do the trick. Money and improved performance, just like I showed you. You'll see improved performance and lower costs, and that'll tell the story.
Another question.
Not going to let me off that easy, are you?
In the design of geosynthetic reinforced retaining walls, the length of the reinforcement is typically the same from the top to the bottom. When you do the calculations for the required length, you equate the pressure that has to be resisted by that particular reinforcement to the amount of friction that you can get. When you do this, the length that you get becomes independent of the vertical stress. And so then the length is a constant. Then you show the failing wedge, and we probably don't want to count the length of the reinforcement that would exist in the failing wedge. So then how do we have a failing wedge that increases like this towards the top? And it seems to me that it should be the failing wedge plus the required length.
You go back beyond for pull-out. That's the case where it's going to pull out at the top. You go back beyond the assumed failure surface, and typically we take the Rankine surface. I think it's wrong. It probably ought to be back a little, and then go back some 3 feet, a meter, and unless you have very, very high surcharges at the top of the wall, it'll never pull out. It'll fail in tension before it'll pull out. So why do we build at constant height? well, or constant length? Well, largely that's a construction expedient. And if you have a rock behind or some reason that you don't want to go back, you probably don't have to, as long as it's long enough so that it won't slide. If there's no earth pressure back there, in other words, if it was a rock back face or something, nothing pushing on it, it's not going to go anywhere. So that just depends on how much you need to make sure that it isn't going to move laterally. So I don't know if I've answered your question, but I think, so it turns out you need the length at the top for pull out, the length at the bottom for strength, and it's just easier in a lot of cases just to go to constant length all the way up. It avoids mistakes too. One of the Glenwood Canyon walls in Colorado, they got the reinforcement upside down. They had a different lengths, and darn if they got it upside down. You know, well, somebody got the plans upside down, and yeah. It still didn't fail. It didn't move. You know, it was just amazing, amazing. We're way too conservative in our design procedures that we have.
Professor Holt, that was a most entertaining presentation. And I could think of all kinds of things I'd like to say when I got up here. But I was one of the engineers who went to Seattle.
Oh. So did Bill Shannon have it right that the
Bill Shannon had it right. I was up there doing direct shear tests, but
Okay.
That was when I first went to work for my dad.
1961 or 2 maybe?
60.
60, okay. Yeah.
And I thought of half a dozen projects where the reinforced slopes either could have been used or have been used. And of course, Texas Department of Highways uses it extensively.
Yeah, that's right.
This plaque is from the Texas A&M University Department of Civil Engineering, and it recognizes Professor Robert Holtz as the 9th Buchanan Lecturer, and thanks him for delivering his lecture entitled Geosynthetics for Soil Reinforcement on November 9th, 2001. Thank you very much.
Thank you. Thanks so much. Oh, thank you very much. Thank you, ladies and gentlemen.